Hello, everyone. Today we're going to start Unit 5 with the section on lines and length. This is actually section 5.2. We are skipping 5.1 over angle measurement. So lines are understood to be infinitely long. It is usually more practical to look at just one part of a line where we can define a clear starting and stopping point. A line segment is the portion of a line that lies between two specified points. We call those 2 points the endpoints of the line segment. This line segment here we can name as either segment GH or segment HG. Unlike a line segment has a finite measurable length, which we define as the distance between the two endpoints of the line segment. We simply denote the length of segment GH as GH. Points are dimensionless objects, so they do not provide a useful way of measuring length. There are an infinite number of points on any line segment. Instead, we define the length of a line segment in relation to some standard length. You're already familiar with several such standards. The inch, the foot, the yard, and the mile are the 4 units of length in the US customary system of measurement. Of course, comparing a line segment against 2 different standards of measurement will produce 2 different numerical results for its length. This is why it is always important to attach the unit to any measurement. This is also why it's possible to convert a measurement given under 1 unit to a different unit of measure. We do this by using conversion factors. Length conversions in the US customary system that you should know are 1 foot equals 12 inches, 1 yard equals 3 feet, and 1 mile equals 5,280 feet. The key to working with conversions is to remember that you can divide both sides of an equation by any given non-zero quantity, giving a ratio which is equal to 1. We can multiply any quantity of 1 without changing the value of that quantity, even if the 1 takes the form of an ugly ratio. For example, we know that 3 over 3 equals 1, or x over x equals 1, or giraffe over giraffe equals 1. Since 1 foot equals 12 inches, and 1 feet and 12 inches are equal to each other, that means they are in effect the exact same thing. So 1 foot over 12 inches would also equal 1. If we need to write the measurement 63 inches in feet, we can multiply times 1 without changing anything. So up at the top here, we have 63 inches equals 63 inches times 1. We believe that. We can then say that 63 inches times 1 foot over 12 inches is also 63 inches. We're just, instead of using 1, using one of our conversion factors. We would want the conversion factor of inches in the bottom because we need it to cancel with inches on top. 63 inches is the same as 63 inches over 1. Inches over inches cancel each other out, leaving us with just feet. So putting this together, 63 inches times 1 foot is equal to 1 times 12 inches, or 12 inches. Inches cancel away, leaving us with just feet. 63 feet over 12, or 63/12 foot, is 5.25 feet. In the US customary system, we often write measurements using feet and inches rather than decimal feet. For example, in the last problem, we were left with the division 63 over 12 feet. When we perform this division, the quotient will be a whole number of feet and the remainder will still be in inches. So 63 divided by 12, 12 goes into 63 5 times. Multiply around the corner. 5 times 12 is 60. Subtract 63 minus 60 is 3. The 5 is now in feet, but the leftover 3 is still in inches. So we could write this measurement as 5 feet, 3 inches. Working in the other direction, we can convert a measurement in feet and inches to just inches by converting the part given in feet, then adding the part given in inches. For example, to rewrite 4 feet, 7 inches as inches, we first convert, then add. So let's deal with the 4 feet first. 4 feet is the same as 4 feet over 1. Since feet is what we want to get rid of, we need a conversion factor with feet on the bottom. Since we want it in inches, we need inches on top. Feet cancel. Feet on the top, feet on the bottom, cancel away, leaving us just inches. 4 times 12 is 48. 1 times 1 is 1. 48 over 1 is just 48. And that part is now in inches. Since the 4 feet is 48 inches and we had 7 more inches, we add the inches together. 48 plus 7 is 55 inches. Let's talk about perimeter and circumference. Excuse me. The perimeter of a figure is the distance around the outside of it. The classic example of perimeter is the fence around a yard. So example 1. A homeowner wants to put a chain link fence around his property. If the lot is rectangular, measuring 40 feet by 25 feet, how much fencing will the homeowner need? Let's go back to our old friend, the 4-step problem-solving process. By this point, we don't really need to go through the 4 steps. We kind of naturally do it as we solve the problems anyway. But since one of the outcomes of the course is that you are going to be thoroughly familiar with the 4-step problem-solving process, let's go through it this way anyway. Step 1, understand the problem. To understand a situation involving spatial reasoning, we always draw a picture. In this case, we have a rectangular lot. We need fencing around it. And the lot measures 40 feet by 25 feet. So the longer length of the rectangle, top and bottom, is 40 feet. The shorter length of the rectangle, left and right, is 25 feet. Step 2, devise a plan. We recognize that the fence should be installed around the perimeter of the property. Thus, our problem is simply to calculate the perimeter of the rectangle. Perimeter is distance around. So we add up 40 feet plus 25 feet plus 40 feet plus 25 feet. Imagine taking a starting point and then walking around, taking every measurement as you go until you end up back where you started. 40 plus 25 plus 40 plus 25. Adding those together gives us 130 feet. So looking back at our result, the homeowner will need 130 feet of fencing. There is, of course, nothing to require that a figure has a nice shape. Consider the figure depicted here. Again, the trick to finding the perimeter is to make sure we don't get lost along the way. Pick a corner to start and mark it, and then make your way around the figure, stopping where you started. You don't want to get confused as to where you started. That's why we're going to mark, in this case, the bottom left corner of this figure. Moving counterclockwise, let's write down the lengths of each side, and then we'll add them all together. 4 plus 1 plus 1 plus 4 plus 3 plus 2 plus 2 plus 3. And now we're back where we started. We add those numbers together, we get 20. So the perimeter of this shape is 20 inches. Perimeter is just distance around. A figure can also be misleading by implying that you can assume symmetry. The opposite sides of a rectangle always will have the same length, so there is no reason to mark all of them. A figure may also confuse things by using inconsistent units. So here, the bottom and right sides of this rectangle are labeled, the left and top are not. We can infer based on the fact that it is a rectangle, 4 right angles, that the top is also 1.5 feet and that the left is also 8 inches. Notice what I said. Notice what it says. Feet and inches. The units are not the same, so we can't just go 1.5 plus 8 plus 1.5 plus 8. We have to choose whether we're giving our results in inches or in feet, and then convert the other value. Since 8 inches doesn't even make up a full foot, it makes more sense to turn the 1.5 feet into inches. So 1.5 feet is the same as 1.5 feet over 1. Feet are currently on the top. We want to get rid of feet. We need a conversion factor with feet in the bottom. Since we want to be converting to inches, we need inches on top. Feet cancel, just leaving us with inches. So we have 1.5 times 12, which equals 18. So 1.5 feet can get replaced by 18 inches. Now let's start our walk again. 18 inches plus 8 inches plus 18 inches plus 8 inches. Now we're back where we started. If we add those up, we get 52 inches. So the perimeter is 52 inches. Now a circle is the shape formed by all points a fixed distance from some center point. So this center point right here, imagine coming off of that point, you had a string, and on the end of the string, you had a pencil. And without moving that center point, you moved the string all the way around. What the pencil would do is then draw a circle. A diameter of a circle is any line segment that passes through the center. So diameters have to go exactly through the center. Straight line from part of the circle to another part of the circle that goes in a straight line through the center. So this marked line would be a diameter, or this line I'm drawing with the cursor right now would be a diameter, or the line that I'm drawing through the circle with the cursor right now would be a diameter. They're all straight lines that go through the center of the circle. A radius is any line segment having as its endpoints the center of the circle and a point on the circle. So remember back when I said string coming from the center, pencil on the end, the string as it makes its way around the circle would be showing you all of the different radii, plural of radius. The string would always be a radius of the circle that's getting drawn. One radius of the circle here is labeled as R. So what's this circumference word, perimeter and circumference? Well, the circumference is just the distance around the circle, just like perimeter is the distance around any figure. Basically, circumference is a special word meaning perimeter of the circle. In the earliest history of mathematics, it had already been discovered that the ratio of a circle's circumference to its diameter is constant. That constant later became associated with the Greek letter pi. So the ratio of a circumference to a diameter always gives us pi. If we multiply both sides by the diameter, we get circumference equals pi times the diameter. Since the diameter of a circle must be twice its radius, we can also say that circumference equals 2 times pi times the radius. So C equals pi d and C equals 2 pi r mean exactly the same thing because d is 2r. We can use either version of the formula depending on what's easier, what we have. Do we have a diameter or do we have a radius? So example 2. A gardener wants to put a decorative border around her circular flower bed. If the flower bed measures 4 feet across, what length of border will she need? So let's understand the problem. To understand a situation involving spatial reasoning, it always helps to draw a picture. So we're drawing a circular flower bed, which measures 4 feet across. We recognize that the border should be installed around the circumference of the flower bed. Thus, our problem is simply to calculate the circumference of a circle. Since we have the distance across, we have a diameter, we substitute into the formula C equals pi d. C equals pi times 4 feet. For pi, we're going to use 3.14159, and we're going to multiply by 4 feet, giving us 12.56636 feet as the circumference. So the gardener will need 12.57 feet of border for her flower bed. Now, had we used 3.14 for pi, the answer would have been 12.56 feet. The more digits of pi we use, the more accurate our answers are. If we had bought 12.56 feet exactly of fencing, that's bold, that we're not going to screw up, but we would have ended up 0.01 feet short. It would not connect. But if we had 12.57 feet of border, we'd be able to make it all the way around. So the more digits of pi we use, the more accurate our answers are. Let's talk about the Pythagorean theorem. The Pythagorean theorem involves right triangles. So let's talk about what a right triangle is compared to other different types of triangles. We can classify triangles based on their largest angle. If a triangle has only acute angles, angles smaller than 90 degrees, it is an acute triangle. If a triangle only has one right angle, exactly 90 degrees, it is a right triangle. If a triangle has one obtuse angle bigger than 90 degrees, it is an obtuse triangle. So right triangles, what we're going to be taking a closer look at, have one right angle in them, a 90-degree angle. In this figure, we see triangle ABC with right angle C. The lengths of the 3 sides of the triangle are named by the angle opposite to that side. So angle C is opposite side C. Angle A is opposite side A, and angle B is opposite side B. Or instead of side B, we can call it segment AC with length B. Or we can call it segment AB instead of side C with length C. opposite angle C. We call the two sides of the triangle which are touching the right angle the legs of the triangle. So the legs have measure A and measure B. We call the side opposite the right angle the hypotenuse of the triangle. So the hypotenuse is opposite the right angle, and the legs are touching the right angle. The Pythagorean theorem tells us the square of the hypotenuse of a right triangle is the same as the total of the squares of its legs. Algebraically, that is a squared plus b squared equals c squared. Example 3. A 12-foot post will be held up by 6 guy wires, each anchored 5 feet away from the base of the post. How long should each guy wire be to ensure that the post is exactly vertical? So the key to this problem is realizing that each guy wire is going to form a right triangle with the ground and the post. We're told that the post is 12 feet. We're told that the wire is 5 feet away. And the wire goes from this point 5 feet away up to the top of the post. The fact that there's 6 guy wires is not relevant to this problem. So the legs of this triangle that are formed are the 12-foot post and the 5 feet of ground. The hypotenuse is the guy wire. We can find the missing measurement of the right triangle by using the Pythagorean theorem. A squared plus b squared equals c squared. A and b are the legs. So A is 5 feet, B is 12 feet. We have 5 feet. We're going to square that. And then we're going to add whatever the square of 12 feet is. And that's going to equal x squared, because our unknown x is the hypotenuse C. When we square 5 feet, we get 25 square feet, or 25 feet squared. Feet times feet is feet squared, just like x times x is x squared. And then when we square 12 feet, we get 144 square feet, or 144 feet squared. 25 square feet plus 144 square feet is 169 square feet, and that equals x squared. To get x, we have to undo squaring. We use the square root on both sides. The square root of x squared is just x. The square root of 169 square feet is 13 feet, because the square root of 169 is 13, and the square root of square feet is just feet. So x is 13 feet. Each guy wire should be 13 feet long. Example 4. Casey wants to use a 10-foot ladder to reach the roof of a building. How far away from the building should the base of the ladder be placed so that the top of the ladder rests on a convenient support 8 feet above the ground? So again, the key to this problem is realizing that the building, the ladder, and the ground are going to form a right triangle. The hypotenuse of the right triangle that we draw out is the 10-foot ladder. The ladder is leaning from the ground to the support. The support is 8 feet above the ground, so 8 feet of the building makes up one of the legs. The other leg would be the ground, and we're asking how far away from the building should the base of the ladder be placed. So this distance is our unknown. This time we're going to use the Pythagorean theorem to find the distance that is one of the legs instead of the hypotenuse like we did in the last example. So again, we start with a squared plus b squared equals c squared. And this time we only know one of the legs. Let's call it A. We could also call it B and have A as the unknown. It won't make a difference. We'll still get the same X in the end. But again, I'm going to use it as A. So A squared would be 8 feet squared. B squared is our unknown squared, so X squared. And then C squared is the hypotenuse squared, so 10 feet squared. When we square 8 feet, we get 64 square feet. When we square 10 feet, we get 100 square feet. So 64 square feet plus x squared equals 100 square feet. Subtract 64 square feet from both sides to get x squared by itself. 100 minus 64 is 36. So we have 36 square feet. And then to just get x, we take the square root of both sides. The square root of 36 square feet would be 6 feet. So the base of the ladder should be placed 6 feet away from the building in order to reach the roof, which is 8 feet up. That's this section. I'll see you next time.